Hi, I'm Ben-Yaakov. This presentation is entitled A Self-Adjusting and Economical Switch Capacitor Balancer for Serially Connected Power Storage Cells. This work was carried out at IRP Systems in Israel in collaboration with Stas Tichkin and Evgeny Smidochkin. The conventional approach for balancing a serially connected cells like lithium ion is by passive balancing. In this case, we look at the batteries, actually measure the voltage, and if one of them or a number of them are higher than the others, then we actually drain the power, the energy, by turning on a bypass path in which we actually losing this extra charge or energy by heating up the resistor. Now this process of course is lossy, and in order to operate it you need to measure all the cells, each one of them. And of course there could be quite a number of cells and they are at high level, so you have to translate this information to the microcontroller. And then it can only adjust an excess energy and it cannot replenish a cell which has a lower energy or power stored in it. And of course it requires a high side drivers to operate all these transistors. Another approach is to use a switched capacitor, in which case we have capacitors which are actually connected to one cell and to the adjacent cell, like here and here. And we can see the operation here. Suppose the voltage of B2 is higher than B1, then when we connect B2 to the capacitor, it will be charged to just about B2, and then we connect it to B1, it will transfer this higher voltage to the B1, transferring energy from B2 to B1. And since we have for every two cells, we have a cell, balancing cells like this, this will balance the whole array. Now the advantage of this approach, as we'll see later on, is that it's relatively of low loss, that is, the efficiency is pretty good. But it takes a long time to stabilize because at the beginning you have a high current, and then this current is going down and down, the average current. So you need quite of a time to balance out the array. It requires many high side drivers, of course, need to measure the cell voltage to know when you are balanced. And another point is that it requires actually a microcontroller. It cannot be autonomous operating by itself. Now, in order to explain the approach that we are proposing in this presentation, and it's discussed later on, I need to cover a little bit the basics of, say, switched capacitor converter or switched capacitor balancer. Information that you can find in my YouTube channel. There are a number of videos covering the theoretical basis of this subject. So if we have a case like this, which actually represents the balancer that we have, we are connecting a capacitor to one cell and then connecting it to another cell, okay? We can talk about three modes of operation. One is that the time at which the switch is on one side, say, is longer than the time constant, and consequently this charging or discharging comes to a completion. Another mode is that the time is very short as compared to the time constant, so therefore the current is almost constant, as if we are just on part of this curve here. And then there is an in between these two, the process has not actually finished, but the current is not constant. We can actually describe this system by an equivalent circuit in which we have a source and then an internal resistance, Re, which, as we understand now, will depend on the frequency. And here it is. These are the analytical solution for this case. What we see here is that at low frequency, at which we are in this region here, then the Re goes down with frequency as 1 over the switching frequency times the capacitor. Here, the resistance of the circuit, okay, does not make any difference because the process comes to a completion, and if we change the resistance, it will just come to a completion earlier or later on, and as it turns out, the power loss is the same. On the other hand, when we reach a certain frequency, there's a break point here, and then we enter the no charge mode, this mode, in which case what is important is the resistance of the circuit. Because here we have a constant current which is limited by the resistance. So what we understand now is along this line we can actually change the resistance, the equivalent resistance of the circuit. So if we have now the two batteries, this is the equivalent circuit, we can now change the resistance and therefore we can control the current, okay? So we can control the current to be actually constant even though the voltages are changing by changing the frequency. Now what about the efficiency? Well, we have the same current passing through these two cells, and power is I times V for the two cells. I drops out, and we end up that the efficiency is a function of the voltages. It's not dependent on the current or on the resistance, which is very nice. We are keeping the efficiency. Now, in the case of lithium ion, we know that the change in voltage between a fully charged and fully discharged cell is about 1 volt, with an average, say, of 3.5. So you might say the average efficiency expected here is in the range of 0.87, which means that only 13% of the energy is lost, okay? And this is, of course, much lower than the case of a passive balancer in which all the energy is lost. So if we operate the system with a constant frequency, we have a high current at the beginning, it tapers off, battery voltages are coming together, and this will be for a constant frequency. If, however, we change the frequency, here it is, then we can control the current to be just about constant, and obviously the balancing will be much, much faster than as compared to here. So this will be a more effective way to balance the array. Now what about the driver? If we use charge pump type driver, having here capacitor, and we have one driver for all the cells, we have a high side and low side, then as the voltage of this pulse train is low, here and here, here we are feeding a negative voltage. This is a P channel, so it will be turned on, while the negative voltage here will turn off this transistor. And on the other hand, when the voltage is high of the pulse, then this will be turned on, the N channel, and this will be turned off. So by having actually one high side and low side driver that is feeding all the cells, we can actually operate the whole array, and this of course is quite a bit of a saving. Now what about the control? Now the intuitive approach would be to control the current, okay, to look at the current of the balancing and then make it constant, control it to be constant. But as a matter of fact, another way, and perhaps a better one, is to look at the temperature of the transistor, because this is what we are worried about. We don't want the transistor to overheat with a very high current, and so we'd like to keep the current about constant. So we can actually measure the temperature and control the switching frequency such as to maintain this temperature constant, and by that we know that we are operating at the optimum point. And finally, there is the issue of how would we know that the system is already balanced, because we don't want to run it continuously all the time if already the cells are balanced. Now here is a suggestion in which we have two extra half bridges, and then we have also sort of a sense resistor, which is measuring actually the current of this low side transistor. So let's see how does it operate. The same driver is also operating these two half bridges. So when the upper transistors are on, we're actually connecting this floating capacitor between here and here at the end of the array. Well, if the lower transistor is on, this and this, then the capacitor is connected between here and ground. Now, if we subtract the two, it turns out that the capacitor is effectively seeing the difference between this upper cell and this lower cell. So here we have a way to tell as to whether these two are equal or not, or balanced or not. Now, if there is a disturbance, or there is a mismatch, or there is an extra voltage or charge in one of the cells, it will spread out. It will eventually get to the end. So if we wait some time and we see that these two cells are balanced, and this we can tell by looking at the current of this sensor, because if they are not balanced, we're going to see spikes here of the current of the capacitor, because we are effectively measuring the current of the capacitor. So when these spikes die out, we know that these two cells are balanced, and this will tell us, if we have waited sufficiently, that the whole array is balanced, and we know that we have now, we can actually turn off this balancing process. And here is a simulation that demonstrates it. Here we have a low frequency. We have some cells, 4 cells, 3 of them have the same voltage, 1 is high. And here is the voltage across the sense resistor. Looking here, zooming in, we see this is the current of the sense resistor. And we see that there's quite a bit of a current, because at this point there is a difference between the cells. Now, when the cells are balanced, there's no difference here, then we don't see any voltage or any spikes, of course, across this sense resistor. Now, if the frequency is much higher, say 100 kilohertz, then of course the current will be higher as compared to the current for 1 kilohertz because of the very lower equivalent resistance. And again, we see here the spikes across the sense resistor, and here is a zoom. In this case, however, because the frequency is high, we actually entered the no charge mode, in which the current is just about constant, and this is why we see this square wave. Of course, when the cells are balanced, again, we don't see any voltage across the sense resistor. So what are the features of this new balancer that I've presented here? First of all, it is faster than the conventional balancer, and secondly, balancing both the high and low cells in terms of energy, as compared to the passive balancer that can only drain power and not add power to a cell. And then we have this charge pump type of a driver, which simplifies matter quite a bit. And then we don't need to measure the cell voltages, because we can tell when the array is balanced. And since this is a very simple operation, this balancing circuit can actually be autonomous. We can add some logic that will turn it on and then wait to see if the array is balanced or not. And if it is balanced, we'll turn it off, and then after a while turn it on, so it can actually go on during operation and balance the cell. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest. Thank you very much.